All right, back to correlation, and when we talk about our correlation equation, how do the numbers work? How do we calculate these little r values that range between +1 and -1 with 0 as nothing? Well, like everything we've looked at so far, the Pearson correlation coefficient, which is what this one's called, is a ratio. And it's a ratio of the degree to which x and y vary together, how much they share their differences from the mean. So if you're high on x, are you also high on y? If you're low on x, are you also low on y? Compared to, or in relation to the degree to which they vary by themselves. So based on how much fluctuation there is in all my height or my x scores, how much variation there is among people in my y or my weight scores. What is the relationship between how much these two things kind of hang together in highness and lowness compared to how much just they kind of vary by themselves? So when we put it into more symbolic form, we have the sum of cross products divided by our sum of squares x times our sum of squares y, and then taking the square root. So we're multiplying our x variation and our y variation. We're taking the square root of those squares. And the sum of the products is composed of this little equation. And it's the sum of for every x and y pair. So for every person, I'm going to look at, well, how are they different from the average height? And I'm going to multiply that by how they're different from the average weight. And if somebody's above average here on height, and they're also above average on weight, well, then they get a positive value. If somebody's below average on height and also below average on weight, they also get a positive value, right? Because a negative times a negative equals a positive. Now, if on the other hand, and that's how positive relationships are, it means if you're above the mean on one, you're going to be above the mean on the other in general. Negative relationships are when you're above the mean on one, but you're below the mean on the other one. So I have a positive value here. If your weight is 150 and the mean is 130, right, you're positive. But then if you are shorter than average, I'm going to start, you're going to have a negative height score. When I multiply this times this, I'm going to have a negative value. And if that's consistent for everyone, my overall SP, or sum of products, is also going to be negative. Questions about that? We'll do some examples. And then my sum of squares x, sum of squares y are just how I've computed in the past, right? I take each deviation score, square, and add them all up. But I do it for x and y independently. So, if we look at this next set, here are my x scores, here are my y scores, right? All I'm going to do is get my deviation scores. I'm going to get my square deviation scores, and I'm going to start adding them up and then multiplying across, okay? So, if we look back at the equation, this is where a whiteboard would come in awfully handy, but I don't have one, so that's all right. My first thing I'm going to do is calculate, or I'm trying to calculate my sum of products. So I need to get my x minus the mean of x scores and my y minus the mean of y scores. So those are my deviation scores, okay? So when I look at this, right, these are my x scores, 2, 4, 6, and 8. And if can I even write in this thing? What kind of table is this? It's one of those Word or Windows to Mac conversion issues. I can't even write in this table. How terrible is that? Well, let's see something once. Maybe. Nope. I'm going to try putting this into Word once. Maybe it'll change the formatting for me. Or maybe it'll freeze up my computer. One or the other. Now if it's saved as a picture for some reason. Oh well. I'll just talk through the answer. So, I add up my x values, right? and I take the average, and I find out that the average is 5. Right? 2 plus 8 is 10. 4 plus 6 is 10. Divided by 10 plus 10 is 20. Divided by 4, I get 5. So x minus the mean of x is negative 3. So if you have these printed out, it'd be good to write negative 3 right here. We do 4 minus 5, negative 1. 6 minus 5, positive 1. 8 minus 5, positive 3. So I have negative 3, negative 1, positive 1, positive 3. Okay. Now I can just go fill in across the way here. I'm going to square these values. So negative 3 squared is 9. 1 squared is 1. Or negative 1 squared is 1, I should say. 1 squared is also 1. And 3 squared is also 9. So if I want to add up my squared values to get my sum of squares of x, I add up 9 plus 1 plus 1 plus 9 equals 20. So my sum of squares x equals 20. Now I'm going to do the same thing for my y-scores. Y minus the mean of y. Well, if I look at my mean of y, my mean is 2.5. Okay? So 1 minus 2.5 is negative 1.5. 2 minus 2.5 is negative 0.5. 3 minus 2.5 is positive 0.5. And 4 minus 2.5 is positive 1. Now I can square those as well, right? And 1.5 squared is, what is that? 2.25, right? Somebody with a calculator check my mental math? Yes. Thank you, sir. So I have 2.25 here. I square negative 0.25, and I square negative 0.5, and I get positive 0.25. I square my positive 0.5 here, and I get another positive 0.25. And then I square my positive 1.5, and I get, again, my positive 2.25. If I want to add all those up to get my sum of squares y, I add them all up, and I get a value of 5. Good so far? All right, now the next thing I'm going to do is do my cross products. And this is to calculate my SP, and that's this last column right here. I'm going to take my deviation score here and multiply it by my deviation score here. Not the squares, but the deviation scores themselves. So it's going to be negative 3, right, times negative 1.5. And then I'm going to put that right in here. So negative 3 times negative 1.5 is positive 4.5. Because again, 2 negatives equals a positive in multiplication. For my second one, I have a deviation score of negative 1. I'm multiplying that by a deviation score of negative 0.5. So that gives me a value of positive 0.5. For my next x score or my deviation of positive 1, I multiply that by positive 0.5, and I get again another value of positive 0.5. And then I lastly multiply 3 times 1.5 and get a value of 4.5. Now for my sum of products, I'm just adding all those up. And when I add them all up, I get a value of 10. Isn't that nice? Fantastic. Now, when I look at my overall equation then, my R is going to be my 10. Well, we came up with 10 for this, right? We came up with 20 for this, and we came up with 5 for this, correct? So this is going to be, my R is going to be my sum of products or cross products divided by the square root of my sum of squares x times my sum of squares y. So that is going to be 10 divided by the square root of 20 times 5 equals 10 over 10 equals what? 20 over 5 is 100. I take the square root of that. I get 10. I divide my sum of cross products by that, and I end up with a value of 1. Which means that these form a perfect line when I graph them out on a scatter plot. And they indeed do. And what this means, again, is that every unit increase in x corresponds to the perfectly predictable unit increase in y. I'm accounting for everything. I can explain everything of everything that happens. Questions about that? Does this equation make sense to you then? If it is, when you think about it, how do I get my strongest possible correlation? Well, if this is the top of the equation, I basically want to make this as big as I can make it. So my x scores that are really high have to be, or I should say my x scores that are really far from the mean on one variable, and then my x, have to be paired with y values that are also really far from the mean. And that's how I maximize the strength, because multiplying a big difference by a big difference gives me the biggest difference I can get. On the other hand, if all my x scores, were extreme and paired with y scores that were right on the mean, so this is 0, well, this adds out to 0, and I've just kind of wasted a very high extreme score that's going to bolster my correlation. And that's where the outlier thing comes in too. When we think about how, where is this? How we look at correlations, and if I had extended, this, but by adding a point way up here, well, that shifts the whole mean up this way. It makes these points more extreme, right? And this point's still pretty extreme. And I'm going to have a much larger sum of products than I would have if that outlier did not exist. Now, sometimes outliers can actually weaken correlations instead of strengthen correlations. When we look at this, right, I could have something like this. And what do you think this is? Strong, weak, or moderate correlation?
Strong.
Pretty strong, 0.83. However, I can add one more outlier right here that weakens it and changes its direction just by adding that one little point. So outliers, you don't know how they're going to affect it. Usually we worry about outliers artificially strengthening a relationship between two variables, but a lot of times it can mask the overall relationship that actually does exist. Because when we look at this, it looks pretty much like there's a fairly good relationship going on there. It's just that this data point doesn't really allow us to. Now, there are other problems with this, but we don't have time to go into them. It gets pretty complicated when we talk about issues of restricted range and whether or not we should oversample from some areas and things like that, but we won't talk about that. All right. All right. Here we go. Settling in. As far as the effect size goes with R, and R again is our correlation coefficient of the Pearson variety, all we do if we want to get our effect size is square it. So R squared is our normal R squared that we've talked about before. And R squared again was the percentage of variance that one variable explains, or I should say the percentage of variance in one variable that is explained by another variable. So like the whole correlation between ACT scores and college GPA being about 0.5. Well, if I square that 0.5, I get 0.25. And that means that 25% of your college GPA can be explained by your ACT score. Doesn't mean one causes the other. Scoring, getting a score on a test does not make you do better or worse. It's really what that score represents that's supposed to be the causal agent. But even so, unless we do some other kind of experiments, we can't say there's a causal relationship. We just say that I can explain some of the variance. I don't know if it causes it or not. I don't know if there's another variable that's influencing it. All I know is that this variable explains about 25% of this other variable, or the variation in this other variable. Likewise, if I had an R, or correlation, of 0.7, well, if I square that, I get 0.49. And that means that 49% of the variability in y can be explained by x. So knowing your x score can let me make a good prediction about where your y score is likely to be. Whether it's something that I don't know about you, something that's going to happen in the future, or any other kind of situation that we might come up with.
In terms of r squared, that's the same idea of strength for effect size?
Yes.
Of being...
Yeah, 0.25 is strong, 0.15 is moderate.
They consider 0.25 to even be strong with it.
R squared, yes. Oh, if you got an effect that big,
yeah,
man, you'd be a rich man about the temperature you're looking for. Yeah, and 0.02 is still small. Some people call it the coefficient of determination. I don't care much for that term, but hey. If you ever hear coefficient of determination, that's what it stands for. That's your R squared, but it won't be on a test in this class. All right, so let's give one more of these a shot. See how it goes. Just by looking at the numbers, though. Positive correlation or negative correlation. Look at the extreme scores on each side. Are scores far from the mean paired with other scores that are far from the mean? Or is there no real relationship between the two? What do you think?
I think it's a weak linear relationship.
Yeah? Positive or negative? Are the high ones on one paired with the low ones on the other? Or are the high paired with the high? And the way that I do this is I look at the lowest number on one side. Well, the lowest x is 1, the highest x is 7. The lowest x is paired with the highest y. In this case, the highest y is 0. And the highest x is paired with the lowest y, 7 and negative 6, respectively. So I would say that it is a negative relationship. I should be looking for a negative relationship. If I don't find one, I should question myself again and see where I went wrong. And I'm not sure how strong that relationship's going to be at this point, though. The fact that the two extremes match up suggests that it'll be moderate or strong, but at least moderate. But we can go ahead and do these calculations here. And why don't I actually put this in Excel so I can... Oops. So I can actually write in this thing 3, 7, 5, 4, 0, negative 1, negative 6, negative 2. Now the only thing you'd have to worry about in this case is when you subtract the negative number. Like the mean for y is -2. So think of subtracting a negative number like adding a positive number, more or less. Hey.
Don't forget negative signs. It makes numbers come out weird.
That's very true. You multiply the deviation scores across each other. Where's my, if you, wait, hold on. I have too many windows open here. Here we go. If you look at this Excel sheet, it's going to be my x minus the mean of x minus my y minus the mean of y. So -3 times 2 is going to be -6.
Oh, so there's less column.
Yes. Yeah. That way you add those up. Those are your cross products. This is your sum of your cross products. And so your sum of squares of x should be 20, sum of squares of y should be 22. Multiply them together. Get your 440, take the square root, run your -19. Divide by the square root of 440, and you should have an r of negative, I don't have my negative sign in here, of negative 0.90 or 0.906 or whatever. Put it in there. Take my word for it. And if we square this to get r squared, we get about 0.82. Now, the nice thing about doing this in Excel is if I want to, I can change or reorder my numbers. And I can see how it actually, let me change that so I can see. I can see how it changes my correlation. Let me just change this to equals this divided by square root of this times this. All right. And just make sure that these are all linked up right. Okay. So if I wanted to make this a weak correlation, the weakest correlation I can make it just by switching two x's around. Which two would I switch? If I wanted to weaken this correlation just by reordering the x values of two of these, which two would I reorder?
Which one would the highest be the lowest?
Okay.
The lowest the highest.
Yeah, well, now will that weaken it, or will that flip it, or what do you think will happen? If I do that, do you think it'll become a positive relationship, but weaker? What do you think? Because you're right, though, that you should look at the extreme scores. And if, say, I just wanted to replace this with the mean, that would reduce the strength of the correlation by a lot. But you want me to switch the 7 and the 1, right? All right, well, let's see what happens. There we go. Now I have a strong positive relationship because the middle values are pretty much all to the mean, and the strength of my relationship was very dependent on those two values, apparently, on those two values. And switching those places has a huge effect on how I conceptualize this relationship. Which kind of steals my next question, was what numbers do I change to make it positive? So if I wanted to weaken it just by changing a number, and I can't change any of the x's, now I have to change the y's. Give me one number to replace and tell me what I should change it to. And it can be a number from 0 to -6. Which one, and I want to weaken this relationship again, get as close to 0 as I can. Which number should I change, and what should I change it to?
Change -6 to something closer to 0.
Well, why don't we change it to 0 and see what happens? That's pretty good. Changing that -6 to 0 gives me a correlation of almost 0, 0.07. And when you think about it, well, now if I'm looking at how my data is paired up, right? My lowest x is paired with my highest y, but my highest x is also paired with my highest y. So that, that's like the person who studied the longest and the person who studied the least getting the exact same score. And I'm trying to tell you that studying makes a difference. And I can't because it seems to not matter, and so on. So that's this is just to kind of see how things change as I change other things about the data. This is 0. Still, that's pretty doggone good. Any questions about that? How these things kind of fit together? I'm not going to ask you to do any math really on the final, but I do want you to understand how these things work together, how when high x's are paired with high y's and high x's are paired with low y's and all that stuff, that's what determines the strength of our relationship. And this is what it looks like on the graph. Now, hypothesis testing with the correlation is just like hypothesis testing with anything else. My h sub 0 is saying that there's no relationship between variables. My h sub 1 says there is. In this case, I'm using the Greek r or rho as my population correlation. So the null says that the population correlation is 0. The alternative says it's not. And that's all there is to it. In this case, my alpha level and my degrees of freedom. Alpha level, I'm still going with that 0.05 or 0.01 or 0.00 stuff. But my degrees of freedom in this case are n minus 2. And I'm losing 2 degrees of freedom because I need a mean for x and I need a mean for y. And each time I calculate one of those, I lose 1 degree of freedom. In the olden days when we were using z-tests and t-tests, I lost a degree of freedom for the mean when I calculated the mean. That then determined what that last value would be. In this case, I have to get a mean of x and a mean of y, so I'm going to lose 2 degrees of freedom. Then I calculate my r and I make my decision. And we're not going to even go through the steps, actually. But the idea is that if my p-value is less than 0.05, then I say that there is a relationship. So let's do some correlations in SPSS because I know that's what you're all waiting for. And I'm tired of the begging looks in your eyes.
We're testing the correlation coefficient and not the slope, correct?
Correct. Slope does not matter at all, unless you have a slope of 0.
Well, would that default to that, though? If there's no relationship, you're defaulting to your slope is 0. Isn't that about the same?
Well, it depends. See, it depends on how close. If you're talking about standardized slope, then yes. But if you're talking about a scale-dependent slope, I could have a correlation of 0.01 that has a slope of 1,000,000, you know. And I could have a correlation of 1 that has a slope of 0.005, you know. So yeah, that's a good question though. Let's see.
That's like the last lesson I teach, so that's why.
Yeah. So open up. I gotta close some windows here. Open up the HSB. We'll say the HSB modified data. What the heck? Where did that go? This way we'll get some relationships. Oh, if I had another gift card, I would give it to whoever got SPSS to open the fastest.
It is something to do with the ants.
Possibly.
I was going to tell Stanley, but that's why.
Yeah, I don't think they heard much of
You
anything.
get a couple of them inside the computer, they can do some damage.
Oh, I suppose that's true. It's warm in there. Oh shoot! Better go get my power cord during the break. Well, these applications are really draining my battery life.
Well, it's probably hooked up to the projector.
Yeah. All the video really sucks the life out of this thing. Yeah, I was surprised they came out with the new MacBook Pro 15-inch with all the solid-state memory and stuff, and the battery life isn't much better. I don't know, but I guess it's doing more too, so they put it in a better processor.
I think they're up against the wall until they get new technology.
Yeah. It's too bad.
Everybody wants smaller and this and that. I have big hands, so I need actually a big laptop.
Oh, right.
I'll have to plug it in anyway because I need.
Right. Yeah. Yeah, I got my phone, if I wanted to text on it, I couldn't. The buttons are so close together and small. It's depressing. Why, I don't know. It just is. All right, I'm going to close some more windows here. Let's see. All right, who's still waiting? All right, well, yeah, anyway, you can, if you want to, we can go to analyze. Well, the first question is, what do you want to see if there's a correlation between something? What do you want to?
Reading scores in math, but that's just me.
All right, reading scores in math. That gets the day. So I go to analyze, correlate, and we are going to go with bivariate correlations. Bivariate means I'm looking at pairs of variables. Okay, so basically I'm looking at, if I could select 3 or 4 variables, but it's just going to look at how each individual variable relates to every other variable, one at a time. So I'm just looking at pairs of variables. So I click on Correlate Bivariate. I'm going to put in, we'll put in the original ones, reading and math. And I will click. Now if you look here, I have other options. Pearson, Kendall's Taube, and Spearman. We're only working with the Pearson in this class. I can do a one-tail or a two-tail test. And then I'm going to ask it to flag significant correlations. Otherwise, I don't have many options with this. I click OK. And my computer is really taking a long time. And I see this strong positive correlation. 0.679 about 0.68. If I square that, I'd be at what, 0.45 or something like that. A pretty strong correlation, right? And that just, if you look at this output, it forms a grid. And we'll throw in a few more variables in a minute and look at how the grid changes and how to read it. But I will have this diagonal here, which really represents each variable correlated with itself. And that diagonal will always consist of ones. And what is on the top of that diagonal is the same as what is on the bottom of the diagonal. So you only ever have to look at either the top half or the bottom half. And here I'm looking at reading scores and math scores. I have this positive correlation. So in other words, if you do well in reading, you do well in math. And it's fairly strong. My p-value is 0.000, which means, again, that if the null hypothesis is true, probability of me getting a Pearson R this big or bigger is approximately 0. Okay? And then if you look up here, I have the exact same thing up here. Same thing. This gives me my p-value. This is the number of observations that I have.
Could you make that interpretation? 46% of your math score is based on your reading score.
Can be explained by.
Fair enough.
Yeah.
But that would go the other way around too.
Absolutely. Right. Because it's a non-directional hypothesis. So in other words, you think that
46% of your reading score can be explained by your math score.
right. And the important thing is we're not saying caused in there. We cannot say caused. So whenever you see caused and there's not an experiment attached to it, red flags and bells and whistles and alarms should go off like crazy. It's not right. All right, so let's go with another one. Correlate bivariate. Again, let's throw in a few more. Let's throw in reading, writing, not highlighting what, reading, writing, math, science, and word problem solving. So we should have 5 things in there right now. So reading, writing, math, science, and word problem solving. All right, and then click OK. My output wants to come up, that would be fantastic. Here we go. All right, so now we have this grid. And if you look at it, right, I have this diagonal of ones, each thing correlated with itself. I don't have to look at the whole grid, I just have to look at either the top half or bottom. From this, what other variable is most strongly correlated with word problem solving? Reading, right. When I'm looking at word problem solving, right, here's the different correlation with the other variables. The strongest one is with reading. Almost a perfect correlation. I mean, that's a humongous correlation. This is real data again, so it makes sense. That if you understand the sentence structure and what a question is asking, you'll be able to figure it out. What is the weakest relationship between two variables? What two variables seem to have the least to do with one another? To represent the most distinct or different ideas or abilities.
Word problem or word solving, problem solving with. Is that what you're still asking about?
Oh, I'm asking for anything.
Oh,
But yeah, well, in word problem solving, which would it be?
writing.
Writing, right. And the weakest one would be science and writing. They seem to have the least to do with, they're still strongly related, but very distinct skills, not a lot of overlap, which is interesting. And if you look at it actually, if you look at the average correlations between each set, writing actually is the lowest. I mean, it seems to be the least related to all the other scores. And again, this is real data. So that says something to you about how cognitive skills kind of overlap somewhat with a mix of cognitive and psychomotor skills, and how understanding is different from producing. You know, when you think of writing scores, you are composing something, you have to follow all these rules that aren't necessarily tied to how well or clearly you think about things. It's a certain form that you have to find about reproducing your ideas on paper.
Isn't that what they're trying to change?
I hope. Yeah, you would think, and well, it's the emphasis on writing in particular. You know, a lot of people will say, and I don't know how, I have to look at the
Well,
research.
that would
on
go
it.
to the measures of how you're measuring this, that those are probably multiple choice tests, or you don't have to write much, you're choosing an answer.
Absolutely. And then except on the writing portion too, in a lot of cases, now you have to write something, and it's a totally different task, very loosely structured, and you get some kind of score on it. Of course it'll be least related. Yeah, very, very good points. Let's do one more and relate. Let's throw motivation and locus of control in there. But let's put them right at the front. So we're going to put them in and we're going to move them up to the top of the heap, and that'll make it easier for us to look at them. So motivation and locus of control, drag them right up to the top. And what are your expectations? Do you think people with higher motivation will have higher scores? Do you think that people with a more internal locus of control, where they feel more in control of their life, will have higher scores? Or do you think they'll have lower scores because they're more independent? And people who feel like the world is always telling them what to do are the first to fall in line and do what they're told. Be a good student. Well, let's run it and find out.
Since almost all of these come up as being significant.
It's because we have 600 people.
Right, okay, right.
Okay.
Do you just wind up comparing to each other because it's all...
Well, you know, if you get enough people, everything's going to be significant. So you do the R squared. You know, like you think of science and motivation. Where you square that, you get about 1%. And that doesn't really matter. So 1% of my science score depends on motivation. Yay. Whoop-de-doo. I don't really care about that. And if you look at all of these, even maxing out right here, you know, that's about 5%. or 6%, thank you, of the variation in motivation, or writing is determined by your motivation, or can be actually not explained by your motivation. And it's hanging around that in a lot of areas. It is positive, so that says something. And if we look at locus of control, the higher your locus of control, or the more external your locus of control, actually, the higher your achievement scores are. And again, this could be a socialization thing, where people who feel like the world tells them what to do and are always doing things out of obligation are doing things out of obligation. And you study hard because you're supposed to.
Which were the females?
What's that?
Which were the females from the
Oh, right, which were the females from last time. Yeah, and then they're the better students. Interesting. Yeah, and the people, maybe, the males, the dumb males, we can call them that, right? Stupid guys. They have less, or I should say, a more internal locus of control, and maybe they don't care as much about studying. And when I think back to my grade school career in particular, that seems to fit. The girls tended to get much better grades than the boys, but they also seemed to care much more than the boys. I mean, I didn't really care about my grades until high school. That's weird. Yeah. Well, I had nuns yelling at me all the time. I had other things to worry about. Sister Marita stabbing me in the back with a pin. Always on my mind. She didn't stab, she just pressed really hard until you cried. You know, those are the good old days when teachers could hit kids and it was okay. All right, questions on how to read this stuff. All right, in that case, it's time to take a break. I'm going to go get my power cord from my office. And if you have, I'll be back in a little bit.
You should pause your recording.
Thank you. If I am recording anything, where is my, should be a button up here. Well, how do I quit it? Well, there we go.